Hello. Good morning, everyone. On behalf of Department of Electronics and Communication Engineering and SJC MATLAB, I welcome you all for the 13th webinar of ECE webinar series. Today's webinar on modeling signal processing and communication systems using MATLAB is from our esteemed resource person, Mr. Shashi Kumar from Corial Technologies, Bengaluru. May I now request Ms. Nandini Maninarayana, Coordinator of SJC MATLAB, to welcome everyone.
Good morning all. I'm very happy to welcome you all for the 13th webinar of Department of ECE on modeling signal processing and communication systems. Signal processing, the enabling technology for the generation, transformation, extraction, and interpretation of information via electrical signal, is essential for our smartphones, wearable devices, healthcare technologies, and digital equipment. Today, we have with us Mr. Shashi Kumar, GK, Application Engineer, Corial Technologies, Bengaluru, to provide practical insights on MATLAB communication toolboxes. On behalf of management and staff of SJEC, I extend a warm welcome to Mr. Shashi Kumar to this webinar. Also, I welcome Dr. Jagdisha R. Bhatt, Associate Professor, and Ms. Rashmi H., Assistant Professor of ECE Department, to be the panel members for this webinar. Lastly, I welcome to all the participants, and I request all the participants to make use of this webinar. Thank you.
Thank you, ma'am. We welcome you too. May I now request Dr. Jagdish Bhatt, Associate Professor, ECE Department, to introduce the resource person to the audience.
Yeah, good morning, everyone. I'm delighted to introduce today's speaker, Mr. Shashi Kumar JK. Mr. Shashi Kumar is the application engineer for MathWork products at Corial Technologies, Bengaluru. Mr. Shashi Kumar holds a BE degree from PES College of Engineering, Mandya. His research interests include medical signal processing, IoT, AI, and product development. He has more than 3 years of experience in embedded system and software system integration. So once again, I welcome you, sir, to this presentation.
Thank you, sir.
Hello. Thank you, sir. Before we begin, I would like to share some guidelines regarding the webinar. Your audio and video are muted. In case you have any questions, kindly put it in the chat. We will address them at the end of the session during QA. A feedback link will be shared. Kindly fill them. An e-certificate will be emailed to you at the earliest. May I now request the resource persons to kindly take over. Over to you, sir.
Thank you, Mom. So, welcome all. Thanks for being part of this webinar on signal processing and communication systems. Before I start, I would talk about the MathWorks license, which is associated with your college. Let me just share my screen. All right. So this is the master license. So I'll just give you an overview of what products you have. and students who are part, or the participants who are part of this session, can also run along with me some examples using the MATLAB online interface. So I'll just give you a walkthrough of how you can get associated to this license and how you can open MATLAB online and start working and executing examples. All right. So you just have to go to Google and type SJC MathWorks. So this will open up the MathWorks campus portal for St. Joseph College of Engineering. Right. So this is the email ID here. So MathWorks Academia TH portal St. Joseph Engineering College. Right. So this will open up the portal. So this is where you can get associated with the license. All right. So these are all the list of products. So can I mean, I'm this sorry. This is for all the departments here. So the participants here, I'm sure will be mostly from electronics. Am I right, ma'am? So can anybody correct me, or can I know what all department students or and faculties are being part of this also? If you can put it in the chat window also, it should be fine.
Sir,
Yes, ma'am.
so mainly ECE department and electrical department. Some students are from CS also, sir.
All right. So thanks, ma'am. Thanks for the info. So basically, MathWorks has coverage for most of the departments here, right? So these are all the toolboxes you have. So, and to get associated with these licenses, you just have to sign in using your SJC domain email ID, right? So you have to be very careful here. So you have to use only your domain email ID, right? Yeah. So with the campus-wide suite, these are all the complete set of licenses you have. So you can see that it is for total academic headcount. So everybody in your college, staff, student, anybody who is associated with your college and who has the domain email ID, which is sjc.ac.in, can get associated to any of these licenses, right? So using these licenses, you can set up multiple labs for how many other departments you want across your college, and each individual also get access to MATLAB, and and even for their personal systems as well, not only for the college systems. All the individuals can get associated to license for the personal systems as well. So you can also set up an infrastructure for parallel server where you can run high performance. If you're working on a big project and you want to execute it, and you can set up parallel servers, a main HPC system. So Polyspace is a software where you can verify your uh, embedded systems code. So if you're working on embedded systems or C code, or for a computer science department, if you're involved in coding, right? So at some point in time, if in the product development, you should test these codes, right? So for certain scenarios, whether these things will work or not. So Polyspace is an interface where you dump in your developed code and test it for multiple scenarios, like thousands, millions of test scenarios you can test using Polyspace server. All right. So web app is again an application development a license where you can collaborate with other researchers from different colleges or different agencies. Like if you're working with defense projects, you can get associated with them as well and give them access to web app server, and whatever they work, it can be collaborated within your campus. Similarly with the production server. So Roadrunner is a new product. So what this gives you is to simulate automated driving systems, driver assistance systems, and simulations, right? So you can explore these. So MATLAB Grader is majorly for faculties, especially now in this pandemic, since everybody is moving towards online classes and online tests, right? So MATLAB Grader is such an interface. So what this gives you faculties access is to teach students using MATLAB. So, for example, the courses might be signal processing or communication. So this is majorly for faculties. So we'll be very happy to address all the faculties and show you what the capabilities of MATLAB Grader, where you can automatically assess all your students just by sending them out links to the questionnaires, and in a given duration of time, they'll have to take this test and submit their answers, right? So this is such an platform, and this is majorly for faculties, and ma'am, we can work with you and get a session on MATLAB Reader as well for the faculties of your college, right? So apart from this, the last one is the online training suite. So everybody who gets access to this license has as a set of training resources available for them to work with. So starting from MATLAB and programming and to data science as well. Let me just show you how it looks like. Right, so this is the MATLAB and Simulink training page. Right, so this is yeah. So you can see that these five are free of cost, so you don't have to get associated with any license. You can simply work on them. So these are core MATLAB fundamentals. So this is a complete 20-hour full stretch in-depth course on MATLAB. So if you want to strengthen your MATLAB skills, just go through this course. So it is completely self-paced. You have videos, you have an execution environment as well, where you actually execute commands, and then once you properly write the logic, then only you'll be going forward, right? So this has everything which has to do with MATLAB and its programming environment, right? So similarly, you have for data science and machine learning and deep learning, right? So see, for data science you have machine learning and deep learning. So this is again in-depth course, 20 hours in-depth course. So this majorly deals with the algorithms on the machine learning, and this is completely on neural networks. And you can extend deep learning capabilities to signal processing, image processing, computer vision, robotics, AI as well, right? So doing these two courses will give you a good strength on AI, and after completing these courses, you'll be capable of developing a deep learning system or a machine learning model. It might be hardware or a software, and you can integrate them and build your own custom projects, right? So if you want to understand some concepts or some theoretical concepts which is completely on mathematics, right? So these courses are help you to develop your mathematical skills in a programmatic way. Right, so using the MATLAB programming language, you'll be solving all the aspects of uh, mathematics, such as linear algebra, nonlinear equations, partial differential equations, ordinary differential equations, integration, differential equations. So pretty much everything you can get trained by going through these courses, right? And this is for financial, if anybody, if there's an MBA department at your college, so you can also go through these courses. So this is completely free of cost, so you people have unlimited access to these things. I would suggest you all to make the best use of it, so that this suit is limited, so you can see that it expires on a specific date, right? So after that, I'm not sure whether you'll get access to this, right? So these are all the training resources you have for your college, and every student, every faculty has access to these courses. So feel free to use this and work on it, and you can enhance your skills as well, right? So any questions for me with respect to how to get started with MATLAB and how to work with it? Do I have any questions? Any questions? Okay, so this is the
No, sir.
sure, thank you. So this is the online MATLAB which you can run. So right now, students who are interested and want to do a hands-on of the examples which I show, you people can quickly open up MATLAB online and get started with it. You don't have to install any software as such. All you have to do is get associated with the MathWorks license, and you'll get access to MATLAB online. Right, so here again, it is very similar to your normal MATLAB interface, software interface, and you have an option of working with Simlink as well. Right, so you can, I mean, I'll be talking about Simlink also today for communications modeling. So you can model using these blocks. Right, so this is how you can get associated with it. If you have any challenges, please post the questions, and I'll be happy to show you all this. So yeah, so this is what I had to talk about what your college has access to, and if you have any queries or if you want any help on any of your toolboxes, you can reach out to me, and I'll be happy to help you all. Right. Right. So moving ahead, let me go to my presentation. So, so the main agenda for today is signal processing and communication systems modeling using MATLAB. Right. So I'll be using two languages again, which is MATLAB and Simlink. So Simlink is a model-based design environment, and I'll be covering roughly around for the next 40-50 minutes. I'll be talking on the signal processing using MATLAB, and the rest of the session I'll be talking about model-based design and how you can work on communication systems, how you can model these communication systems and verify them. All right. So if I'm going fast or slow, just please let me know. If you have any questions, just raise your hand and you can interrupt me and such. All right. So this is the agenda I have for signal processing. Right. So I'll give you a small introduction on what signal processing, where you can find signal processing applications. So the first step is to in MATLAB or any where is to have the actual physical signal to test and perform, do some analysis on, right? So I'll be talking about what are all the different signal generation functions you have to generate signals and how you can measure them. So then I'll be talking about signal filtering, and I have an application example which talks about signal filtering and the different aspects of signal processing toolbox. And I'll be talking on multi-signal processing and some common application examples which can be done using signal processing toolbox. Right. So we know that signals are everywhere, right? So we use it in our day-to-day lives, and yeah, everywhere around we have signals, right? So majorly we use our mobile phones, so we use it for communication, right? So for example, communications and radars, right? So we for audio and navigation system for in your cars or your audio devices, everywhere signals are present, and we work on signal processing is essential for us to uh, uh, reprocess them and give you the user interface they currently give you right now, right? So medical devices also use signal processing, ECG, EEG, EKG, EMG, and other things, right? So all these things are signals. So in fact, for it is common everywhere around, right? So there are signals everywhere, and one or the other way we have a sensor and we are able to capture these signals. So we'll have to eventually do some signal processing techniques on them, implement on them, and find some insights and work on them. Right. So this is the workflow which we'll be using, and which is also recommended when you are working with MATLAB. Right. So first you'll have to get access to all the files, softwares, uh, which might be from softwares or hardwares. Right. So it might be a text file or an Excel file or a table. any other audio file, image file, video file, anything which is a source can be imported onto MATLAB. You can explore them, you can discover them, and you can ultimately build algorithms on them to accomplish a specific task and develop applications which can be deployed on mobile phones or hardware device, embedded hardware or HDL hardware. And it's an environment where you can do end-to-end simulation as well as prototyping, right? So we'll be talking more on the explore and discover part today, and I will how signal processing we can explore and what all functions can be used to explore the signal that we'll be talking today. Right. So once you have these things, if you want to share it across, you can share them using PDFs or Word documents, or you can send the whole design itself. In MATLAB Online, you can simply give access to different people, and you can send it across to their drives and share your work with your colleagues and such. Right. So ultimately, you can deploy them as as a web application, as a standalone application as well. Right. So these are the key features. So this is what we'll be following today. So we'll be accessing some files and discovering them, and we can let's see. I won't be talking about deployment much here. Right? So these are the key features of the signal processing toolbox. I'm sure most of you would have studied signal processing in your engineering and such. Right. So these are the same things can also be done using the signal processing toolbox. Right. So for example, for like signal generation and visualization, you can perform signal transforms. You can implement digital filters and do some analysis on them. You can do statistical signal measurements, and you can do spectral analysis. You can observe the spectrum and see how the signals are and work with them as well. Right. So let's talk about these one by one. So first, let me talk about the signal generation. What are the commonly used signals which we use in our signal processing, and how we can generate them? And let me show you the example. So what I'm doing here is I'm generating a square wave. I'm generating a sawtooth wave, a sine wave, and a chip signal. So chip signal is a signal which increases the frequency as the time increases, right? So what I'm telling you here is it starts from zero point 0.5 hertz to 150 hertz in a period of uh, 0.5 seconds, right? We'll see how this works out. So I'm taking the sampling frequency as 2000, and I'm generating a time scale of the sampling frequency here. And I have I'm generating a 50 hertz signal, right? So that is my frequency, right? So once I implement this function here. So square is the function which can be used to generate a square wave, and sine and sawtooth accordingly. So chirp, like I told you, so from 0 to zero point 0.5, as you reach zero point 0.5, you should reach 150 hertz is the actual meaning here, right? So starting from t is equal to 0 to zero point 0.5, it should the frequency should increase from 0 to 150. Right, so that here you won't be able to make much sense because this is a 2D scale. So once we find a spectrogram here, it will make more sense, right? So as and when the time increases, you see that the frequency is also increasing, right? So MATLAB has functions to simply plot the spectrograms and fast spectral densities as well when it comes to signals, right? So that's how there are many other functions which can be used to generate signals, and you can also acquire and process real world signals as well. So these are some of the hardwares and some of the devices which can be used to acquire real world data, real time data, and push it into MATLAB and do some analysis on it. Right. So and these are on the toolbox which is required. So instrumentation control toolbox allows you to get the signals from these oscilloscopes using RS-232 interface. Right, so data acquisition toolbox also allows you to access many of such as PCI or anything. So image acquisition lets you use your laptop webcam, or you can any other hardware USB webcam if you want to interface and gather some real-time images. You can use the image acquisition toolbox to acquire these images. Right, so similar for vehicle network toolbox and MATLAB. So you can interface these real-time hardware. You can capture those data on MATLAB and do some real-time simulations as well. Right, so using these toolboxes, yeah, you can install the supported toolboxes, supported the hardware support packages for this hardwares, and you can work on them. Right. So let's move to signal filtering. So before I move to signal filtering, let me talk about some of the challenges that we face when we are working with filter design. Right. So the first and foremost is I need to find an application specific filter for my project to create a working system prototype very quickly. Right, so this is one of the challenge. I don't want to waste more time in simply developing a filter as quickly as fast as possible. If I'm able to design an application specific filter, then I can come up with prototypes much faster. Right? So if I want to explore different design methods and filter architectures, right? So I have two, three more or more filter designs, and I want to verify each of them for their performance and their architectures, right? So I want a faster iteration as well. So it should be fast enough and to simulate and give me out results very quickly, right? So there has to be an automated process for me if I'm working with any project, right? So and whatever algorithm I have worked on MATLAB or for example any other simulation software, right? So again, the challenge here is I'll have to rewrite the whole implementation in either C or MATLAB code. So because ultimately, if you're working on hardware, and all they understand is C or and HDL languages, right? So the whole logic has to be implemented in C or HDL or whatever hardware you are targeting, and that is a time-consuming challenge what we have, right? So for these challenges, so these are all the remedies or the part-time solutions which MathWorks has for us to offer, right? So for rapid design, you can, so MATLAB has a lot of application-specific filters which you can simply drag and drop, or you can use the functions and you can work on them simply given the parameters and it will work. Uh, uh, and you can verify your designs and such. So for faster iterations, yeah, there are many different analysis tools where you can actually compare two, three methods of filters. So which I'll also be showing you in very shortly, how you can compare two or three filters simultaneously and observe and uh, compare the results. So so for streamlined design flow, so MATLAB also has a fixed point designer which converts your real-time floating point data to fixed point data, right? So which actually works in the hardware. So like we know that whatever hardwares we use, everything inside whatever data is processing, everything is fixed point, right? So even in a laptop, it is fixed to around 64 bits. So all the iterations should be fixed to a specific floating point for that, so that the hardware support, and when you're processing, there is overflow or there is loss of data or there's no corruption of the data when you're working, right? So and finally, when you want to implement all these designs, MATLAB offers you to automatically generate C code or HDL code for the design filter or the MATLAB program as a whole or a Simulink program as a whole, right? So provided that you use only those functions and toolboxes which are compatible for code generation, right? So MATLAB has many functions which are convertible to C code, but for HDL you have a limited number and you should only be using those blocks which are compatible for HDL code generation. For C code, most of the functions are C code convertible, right? So this is the example I have for signal filtering. right? So I have an ECG signal or EKG signal, right? So now I want to process it, I want to load it and visualize it and make some inferences out of it, right? So how do I do that? So this is the complete workflow here. So this is what I'll be doing in this example. So I'll be loading the EKG signal. I'll look for detrends. So I'll talk about detrends very quickly. So I'll see if there is any trends and detrend it. And once I detrend it, I will perform some low pass filtering because I don't want unnecessary signals to be part of my analysis right? So, and once you do a filtering operation on any signal, it introduces a delay. So I should be doing some delay compensation here. And once I do that, then I'll be visualizing the data here and I'll analyze it and see and extract some of the features what I want to explore. Okay. So this is the okay. So do I have any question?
Sir, please continue, sir.
All right, sure. So yeah, so this is what we'll be doing today. So let me just open the example here. All right. So this I have already captured some ECG signals and I have loaded it onto my workspace here. I've stored it as a file here, right? So what I'll do is I'll just load them and I'll plot them and I'll show you how the actual real-time data looks like, right? So I'm having the sampling frequency of 2009. So this is my so this is the plot of the ECG signal I have here, right? So now one question to you all is if I want to find out the amplitude of this signal, so is it possible for me to calculate it, or what is the amplitude of the signal here? Any guesses? Anybody?
So can I ask a question?
Sure, sure.
So can you tell how we can go for spectral analysis and all?
Yes, ma'am. Yeah. So I should. That's my next thing. How I'll be generating the spectral. So without spectral analysis, I won't be able to do low pass filtering, right? So I'll be talking about spectral analysis as well.
Right, sir. Right.
I'll be talking very shortly. Very shortly. Yeah.
Yes.
That's the next section. Yeah. So here in this particular signal, is it possible for me to accurately measure the amplitude of the ECG signal is the question. Any guesses? Anybody? All right, no problem. So basically, you see that it is not aligned to the zero axis, right? So even though it is slant and such, yeah, but then the difference we can find out, right? But then it is very irregular as we move ahead, right? So first and foremost, if you want to find out any uh, amplitude, it has to be aligned to the zero axis or the zero reference, right? So that is when we can measure how much it is in the negative scale and in the positive scale, right? So that process is called detrending. So I'll be using the detrend function to detrend the signal, right? So I'm just passing the input signal here, and this is the output, right? So you can see that at the zero axis here, I have properly shifted the signal, right? So this is one major problem you'll face when you're working with the real-time data, right? So when you're acquiring some data, the data won't be aligned to a zero axis here, right? So it is very essential for us to actually push it to the zero axis here and then process it, or else the computations what you find out or the values will be inaccurate, right? So now I've aligned it here. So the next one is I can see that I have a lot of disturbance here. I want to smoothen the noise, right? So clearly this means that it has high frequency components, right? So, but let's see first what is the path spectral density of the EKG signal here, right? So I'll be using the p-Welch function, and using the p-Welch function, I won't pass any parameters here. It's just my input signal and what is the sampling frequency, right? So it will plot the frequency spectrum of the signal here, right? So here I can see that most of the signal is concentrated here in the less than 100 hertz section here, right? So now I know that what my cutoff frequency of my filter should be. So I'll be doing a low pass filtering, and let me say around 150 or 100, or I can say 150. I can take it as a conclusion. Looking at the pass spectrum here, I can tell that my low pass filter can be of 150 hertz filter, right? So now my next step is to design the filter. Right. So now there are two ways which you can how you can design the filters. Right. So I'll be spending some time on explaining you all how what other apps you have for filter building. So let me just open it. Right. So the first way is to actually design a filter using a programmatic approach. Right. So you have many functions as part of the signal processing toolbox, and you can simply use these functions to design a low pass filter or a high pass filter or a band stop or a band limited filter, right? So in any filters of any specification you can use using the uh, functions, right? So an interactive way how you can actually design a filters is by using apps. So MATLAB, that's where it stands out. It has huge apps for us to simple the process. So uh, the app I'll be using is Filter Designer, right? So you'll have to go to apps and go to Filter Designer here, and this will open up the Filter Designer, right? So this is an GUI which helps us realize many filters and their responses, and uh, we can also I'll show you what are the things you can do, right? So you can automatically generate a Simulink model from this as well. You can generate HDL code, you can generate MATLAB code, right, from this GUI. So let's see how we can do that, right? So for this example here, so what I have designed here is a Chebyshev type 1 filter, right? So which is an IR filter. So I can click on IR and Chebyshev type 1, and you can specify the order as well. So here I've taken the order as 7, and you can specify what order you want, and the sampling frequency here is 2000, and my password is 75, right? So now you can click on design filter, and this will give you uh, the response of the filter, right? So this is the filter I have. So what I'll do is let me just store my filter as low pass Chebyshev type 1. Right. So now what I want to do is I'm not sure whether Chebyshev type 1 is the best case filter for me. Right. So now I want to compare two or more architectures, two or more filter architecture, and see what their responses are, and then come to a conclusion. Right. So now let me see for of a type, for example, I'll take a Butterworth filter here and provide the specifications. I will specify minimum model. Right, I'll design a filter. So this will again plot the response here. So I'll store it as Butterworth. So you can do the same. Okay, you can try one for FIR. Right. So for example, window. I'll take a having window. Right. So of a specific order, I'll design a filter, and this will again design a specific filter based on having window. So I'll store this as well. Right, so I've stored, so this is how you can store multiple filters using the store filter option. So how do you compare is you'll have to go to filter manager here. You'll have to click on all the filters which you want to compare and click on FV tool. Right, so this will compare all the, put all the three designed filters in the GUI, and you can compare the responses. So this is the magnitude response. You can compare the phase response. Right, similarly for impulse response, delay response, phase response. So you can plot the pole zero plot, right? And you can also get the complete filter information of the filters which you have put in. So this is the complete filter specification. If you want to document it and what it has used, so you can click on. You can get all the information here, right? So this is how you can actually compare multiple filters and take the best desired response, and you can work on it, right? So now you have designed a filter. So now let's see what else we can do, right? So you can see you have multiple options here, right? So so you can create a multi-rate filter. So you can change the sampling rate frequency. You can interpolate it or decimate it, right? Based on the specifications, you can add more simple samples and remove decimate it to remove some samples, and you can perform multi-rate analysis here. So you can also quantize this. So this is a floating data type what I'm using here, right? So the default data type of MATLAB is a double data type, right? So it is all the data what I'm using here will be of double precision floating point, right? So suppose you are working to implement it on a hardware, and there you will require a single precision or a fixed point uh, there, right? So if you are implementing on a DSP chip which is of 16-bit or a 32-bit, you should have the filter arithmetic of this supported filter or the supported data, right? So this is where you can mention, click on fixed point, and you can specify the word length to how many bits the data has to be. And you can click on apply, and it will apply the data, right? So this is how you can quantize the whole filter operation, right? So this will now work only for 16-bit data input, all right? So now you can realize this filter as a Simulink model as well, directly from the filter designer. So this is if you go to the realize model function here, right? So you can what I want. So I'll simply click on realize model. What will this give me is the filter visualization tool is available by default, yes. But you should be having signal processing toolbox. So the filter visualization tool is a part of a signal processing toolbox. So if you have signal processing toolbox installed, you should be getting access to filter visualization tool. All right. So I've just clicked on realize model here. So what will this give me is a Simulink. It will open up a Simulink model if you have already opened up a Simulink model. Upon the same Simulink model, it will put a MATLAB function of the filter implementation. Right, so this might take some time because it is converting the whole filter, double precision filter to single precision filter. Sorry, fixed point precision filter, and then it is automatically generating a MATLAB code, and now that code, it is putting it to Simulink and giving me as a MATLAB function block. Right, so let's see how this works out. Right, so any questions till now on how to use filters and how you can work with them?
Shashi sir, here one question is there.
Yes, ma'am.
Is the filter visualization tool available by default in the MATLAB, or should
Yes,
we
ma'am.
install it in the add-on package section?
Yes, ma'am. So they will require signal processing toolbox to be installed to get access to these apps. So the filter visualization tool is a part of signal processing toolbox, and you should have signal processing toolbox installed, and then only you'll get access to these applications. Or else you won't able to find the filter designer option here in the apps itself. Right? So it is part of the signal processing toolbox. Yeah. So now what it has done is it has created a blank Simulink model, and it has realized the filter form. Right? So if you double click on the filter here, it will be a MATLAB function, the MATLAB function block. Yeah. Yeah. So this is the realized filter. Okay. So you can also get it as a MATLAB function. So now it has implemented directly as a filter function. So this uses the state space model and realizes the coefficients and so the input quantizer here, the convert block, what it does is it converts the double precision point to fixed point. Right. So now you don't want it as a filter, you want to realize the filter as a basic element. So how do you do that? Right. So ultimately a filter here will be a combination of additions and subtractions and delay elements and such, right? So how do we build that is by, I'll just in the same window build a model using basic elements. I'll simply click on that, and it will ask some optimization, and I'll click on realize mode. So what this will do is it will create a filter block using only basic elements like gain, delay, adder, and multipliers and such. Right? So, and it is also of the direct form realization of the filters. So I'll just show you how the filter comes out. So this is my realized filter. So here my filter order is 10, right? So this is what is happening here, right? So it has used only the, so first it is converting the data, and it is using only the basic elements such as delay elements, gains, and multipliers and adders to realize the whole filter. So this is a direct form representation of the filter. Alright. So this is only using the basic elements. So this again, what I did was simply click on uh, uh, build model using basic elements. Right. So you can also do the same for pole zero editor. You can do some optimizations and other things. Right. So now if you want to generate code, all you have to do is go to targets here, and you can generate a C header for a filter here. You can generate a Xilinx coefficient file. You can generate the complete HDL code of the filter itself, and you can also integrate it with Code Composer Studio ID. Right, so if you click on generate HDL, so it will convert the whole filter here to HDL, so which might be VHDL or Verilog. Right, so if you click here, suppose I want to Verilog. So here you have some options of modifying or optimizing the filter, right? So you can select the architecture and what are all the sources, and you can also generate test bench for the filter, right? So the test bench will comprise of impulse response, step response, ramp, chip response. So these are all the stimuli which automatically MATLAB takes into consideration, and uh, you can it will give you out a test bench for you all, right? So what I'll do is I'll just click on generate. So now it will generate two files for me, which is the filter implementation file in HDL and also the test bench to test the filter implemented. Right. Right, so here, yeah, so this is the filter what I have. And it has also created the test bench for me and given. And so if I simply click on this, it will open up the HDL, the Verilog code for the filter, implemented filter, right? So here all you have to do is give a clock input, enable reset of what is the filter input, and you'll get the filter output, right? So it's a complete filter, digital filter. Right, so first we had also quantized it. We made it as fixed point of a 16-bit word length, right? So it has also taken care of that, and it has given the output. Right, so it has automatically created the whole HDL Verilog code for the filter, and this is a test bench as well. This is completely synthesizable code. You can simply copy paste it to your Xilinx IDE, and you can actually run the complete implementation as a whole. Right. So this is a complete test bench to generate the signals and test it. Right. So you can explore them and when you're working on them. All right. So this is what you can do, and many other things. You can also generate MATLAB code. So you can click on generate MATLAB code and filter design function. You can generate the MATLAB code if you're working, and you can import it to your existing MATLAB code here, and you can work on that. Right. So this is what you have for filters. If you have any questions, please feel free to post it in the chat. Right. All right.
So just to add a clarity, just in for students' clarity. So now what we have done is we have taken the toolbox and we have seen the different filters. We could compare and all, and we also exported to the our Link, and we have seen that, right? So now we also know that we can generate a MATLAB code also. So here the clarity, like I wanted to ask, is like the what we generate is a function, right? So
Yes,
what we generate from the tool, what we export, or we generate a function. So basically, that function can be used as a filter function, which the signal, the input signal can be taken and converted or filtered, and an output can be taken, right? So in that.
Yes, ma'am. Yeah. So you just use the input signal, pass it to the filter. It will perform the filter operation.
Yes.
And give it out.
Yes. So that's how a complete system that way can be used. So in MATLAB. So can we put it that way?
Yes, ma'am. Yeah, exactly.
Thanks.
Yeah. So, starting from the process, the example we want to find out and do some analysis on the ECG signal, right? So we first saw that it was detrended, so we trended it. So I mean, detrended it. Sorry, right? So we put it to the 0th axis here, and once we did that, we calculated the power spectral density to see what band and what range of frequencies are available in the input signal, right? So once we do that, we created a filter for them. For that, we designed a filter and for the cutoff frequency of 75. Looking at the frequency spectrum here, and now once we apply the filter, right? So this is how the power spectral density looks like, right? So we can see that after 75 hertz, there is a lot of attenuation of the signals, right? So this is in dB, right? So this is something around minus 90 dB, which is very low signal, right? So now we have the signal of interest at our hand. So now let's see how the filtered signal looks like, right? So this is how the filtered signal. So when I apply the filter and when I just plot it out, so this is how the signal looks like. So blue color is the original signal I had, and the red signal is the filtered signal, right? So you can see that it is a lot smooth and lot of good curves are there, and I can approximately estimate power of each signal present here, right? So what we see here is this the filtering operation what we implemented on the signal has introduced some delay to the signal, right? So whenever you do a filter operation, it introduces a small delay in the output, right? To compensate for the delay, we'll use the field function. We'll just pass in the values, and this is the output. So field function, what it does is it compensates for the delay, right? So the black color signal what I have here is the output of the field function, and this has compensated for the delay here, right? And we can accurately map the input signal, right? So now here you can, when it comes to analysis of ECG signal, usually you uh, take care of the PQRS component, right? So PQRST components and other distance between your PQ and RS and many other things. So when you are doing analyzing the biomedical signal, right? So you can do some analysis very easily right now because you have the completely pre-processed signal, and by visually you can see that you can extract many features from that observed signal. So compared with the signal what we have at first, right? So here we won't be able to make any sense of the input, but whereas once we do a filtering and compensate for the delay, we can extract good features from this, right? So that's what I had for the example of for pre-processing for you all, right? So this is what we did. So we data the EKG signal, we visualized the power content, right? So we designed and applied a low pass IR filter, and then we compensated for the delay introduced by the filter, right? So yeah. So similarly, you can perform multi-rate signal processing. So multi-rate is at a single system you have multiple systems or multiple sections which are having different signal speeds. So suppose you want to process, suppose you have two analog to digital converters, right? So and they are sampling two different signals at two different frequency. So you can model these type of systems as well in MATLAB and Simulink, right? So and you can also like convert the existing signal to a different frequency, sampling frequency as well. So that you can upsample the processes, or you can downsample the signal, right? So you can use interpolation and decimation to actually carry out these processes. So decimation, what it does is it actually skips values by which you actually lose out the sample points from the signal. Whereas interpolation, what it does is it tries to add more signals between two signals, right? So that way you actually end up increasing the number of samples for a particular signal, right? So you can also resample them and you can take care of anti-aliasing effects as well, right? So these are the examples. So let me move to the common applications here. So we saw how we can remove trends from the EKG signal here, right? So you can also detect distorted signal and you can remove the spikes from them, right? So for that, I have a small example. So this is the signal I have. So I have a signal of 180 hertz, which is sampled at 3.6 kilohertz. So yeah, so I the signal here, which is distorted, right? So that is the noisy. So I'm just filtering it out here. So the blue color here signal, what I have is the noiseless input, right? So let me calculate the past spectral density of these signals. We saw that once you calculate, you have some peaks here, right? So let me see. Let me see if I can calculate the peaks as well for the signal, right? So I'll use the find peaks function. So what this function does is it takes a specific threshold. You can also have a limit of how many number of peaks you want in a signal as the output, right? So it basically detects the peaks in a signal, right? So I'm using the find peak signal to detect 4 peaks, which is the first 4 peaks here. Uh, right? So I have a high frequency component here somewhere at zero point 0.6 and the zero point 0.2 is my, so 180 hertz is my input signal, right? So that is dominant, but I also have other frequencies as which are present in the signal, right? So this is how you can detect and you can also remove them. So now you know what are the frequency ranges for your filters, and you can apply the filtering operation and you can remove these filters and you can also verify, right? So you can also remove spikes. So this is majorly observed when you're working with hardware, medical devices or any other devices which is connected to the 230 volts supply, right? So this is majorly seen when you're working, right? So this is my input signal I have, and these spikes are my environmental or the short like spikes power supply effects, which actually affects the input signal. So if, for example, if you are capturing a signal from a patient or any other hardware and it is connected to the 230 volt supply uh, of the house, right? So it has to be properly grounded one, and due to some fluctuations, power fluctuations, it can lead to these spikes, right? So how do I remove these spikes is again the same one. So I'm just using a median filter here and I can use. So basically it's all filtering for your specific type of application, right? So I applied a median filter and I was able to actually remove the filters. Right, so this is a good signal for me to process. Now you can actually treat this and you can also work with. So these are some of the common examples which you, simple examples which you can expect to work with when you are working with signal processing tools. Right, so any questions for me till here? I'll go ahead.
Yes, sir. You can go ahead.
All right. So the last topic which I want to cover here is adaptive filters. So MATLAB also has many functions for you to actually realize adaptive filters, right? So and we know that adaptive filters are used for a wide range of applications for communications as well as signal processing applications. Right. So some applications here is for adaptive noise cancelling, adaptive echo cancellation, and it is used in digital communications and such. Right. So the only challenge here is it is a computive algorithm, and it requires time to compute the coefficients and give you the output. So if your adaptive algorithm is complex, so it will take a lot of time for you to get the result. If your adaptive algorithm is simple and you can get it easily, but then again you'll have different trade-offs as what it might not be able to do, what the complex algorithm was able to do. Right, so these are some of the adaptive filtering algorithms which are part of the filter design toolbox, and also you get to see these in DSP toolbox as well. So let me just see, show you the library process. So here you can actually simply drag and drop the blocks and work it out. Right. So ultimately, MATLAB signal processing toolbox gives you access to work with filter designs. You can also do signal and image analysis, right? So you can convert it to fixed point and realize on hardware. So you can do a system level design using the signal processing block set, which is available. I'll just show you what are all the blocks available in the signal processing block set. And you can convert your Simulink and your filter models or your Simulink like signal processing MATLAB codes to HDL codes, and you can do hardware in the loop simulations as well, and you can link it with other EDAs like Model Sim or Code Composer Studio, and you can verify them there, and you can work with them as well. Right, so this is the DSP system toolbox, and here you have multiple operations here. Right, so suppose if you want to estimate something, so these are all linear section to filtering, and these are all the adaptive filters which are available. So LMS is majorly used because it is very easy to implement and fairly accurate as well compared to other adaptive filters. So you can do math operations on signals and other operations. So these are all drag and drop blocks which you can work with. So if you are very new to signal processing, Simulink environment, no problem. I'll give you a small introduction to model-based design now before starting the communication systems. And even though if you are not satisfied, you can actually go to the Simulink on ramp. And if you complete the Simulink on ramp, I'm sure by the end of the course you'll be able to understand and work with the Simulink environment and use these blocks to build your own projects. Right. So yeah, so this is what I had for signal processing applications. We can quickly move on to communications design. So if you have any questions, uh, please feel free to reach out to me. I'll just wait for 1 or 2 minutes if you have any questions with respect to signal processing, and quickly we can move on to communication systems design.
Sir, I have one thing to ask.
Yes,
So we have seen the toolboxes with the, the filter design, etc. Of course, the students of B, they studied DFT, that the fast Fourier transform, the FIR filter design, and the IIF filter design in their fifth sem. The adaptive part usually they study in the masters, and even we faculty use that. So that part, and of course they study the power spectral density, like to some extent they know about the pole zero plot and the stability of the system analysis, etc. And to speak about FFT, we usually we write the program and check for the the FFT and do the analysis that way. So can you throw some more a little light on how FFT can be used in a real time scenario, and your viewpoint on the usage of FFT, the fast Fourier transform, and in filter design, and how it affects the different points, like the 8-point DFT or 16-point DFT, 256-point DFT. applications we go for, for ECG and all, we go for 512,024 and higher orders of points, right? So
Yes,
can you
ma'am.
throw some light from your point of view regarding this?
Sure, ma'am. Yeah.
The
So, I
FFT
mean,
part, yes.
FFT is major. Sorry, ma'am.
Please go ahead, sir. Please go ahead. Please go ahead.
Yeah. So, I mean, I've been using FFT, I mean, in my previous company, so where I was a biomedical engineer, I was developing medical equipments there. So there usually we used to handle very low frequency signals. So for medical devices, if you ask me, so there the order is very less. Right, so the order is either the sampling frequency itself is less. So either they'll work in 256 or 512 or 102. So maximum they can go up to is 2 kilohertz or 5 kilohertz, because the ECG signals are the EEG signals what we acquire. So their major frequency spectrum lies in from 1 to 5 hertz or somewhere there, right? So that is one application. But when it comes to defense sectors, the signals which you will be actually working, or the signal processing, or if you talk about radar systems or communication systems, so you use the frequency spectrum in a different way there. So you majorly use for FFT to actually calculate the convert the time domain signals to frequency. So there the operation is different. So the filter design is very more higher order, and the signal rate is also more. Right. So there are so this is where you'll usually get to work with FFT in real time. So in fact, my brother is also working, and he also uses FFT big time to write HDL codes and for an application. So if you're working on signal processing, FFT is majorly important because you want to analyze signals and take some inferences out of them, right? So you can also use the signal analyzer here, right? So you can actually load it from the workspace. You can load, oh yeah, so these are all the data here. Right, so what the signal analyzer does is, so without actually writing a single line of code, you can also do the spectrum analysis using the signal analyzer here, right? So let me just see the chip signal here, right? So let me try to plot. So this is a signal here, right? So here, what you can do using the signal analyzer is you have all these blocks already, right? So you can smoothen the signal. You can apply a low pass filter of specific pass band, and uh, you can actually see how the filters will work for these type of signals here. You can also like plot the frequency spectrum directly using the signal analyzer, right? So you can go to display, you can click on spectrum, so this will plot the frequency spectrum and also the time frequency uh, variation of the signal as well, right? So this is a signal, right? So the frequency is increasing as and when the time is increasing, right? So that is also can be seen here. So this is required when you're actually working on applications, right? So I'm from a medical background, so I know very little about radars and how it's up, but I've been studying them. But then FFT is a major funda there, and you use interpolation and decimation also when you're working with signal processing, right? I hope I throw some light on FFT. Is that what you wanted me
Yes.
to talk about?
Yes, yes, sir. Yes.
Yeah, so this is where real time you will get to work with some of the applications uh, on signal processing, right? So big time, whenever you're working on communications or wireless design or any instrumentation, right? So you'll get to work with FFT or signals and spectrum analysis. Do I have any more questions?
So you can continue, sir, with
Sure.
the communication. Yes.
All right. So let's move on to communication systems modeling. Sorry for that. Yeah. So here I'll be talking about how you can model an end-to-end communication system, starting from a transmitter and to a receiver. How you can actually what other techniques are there for communications and such. So the major environment I'll be using today, now is the Simulink. I'm sure most of you are aware of it, and it is a block diagram environment, and it is a uh, block processing environment there, right? So you can model, simulate, you can analyze, and you can validate the dynamic designs, right? So you can convert codes as well. So kind of as an intensive library browser for you all when it comes to, right? So we also saw this, right? So let me just quickly move on. So this is some thing. We were talking about actually we were doing a lot of programming in signal processing, right? So that was a programmatic approach for a solution, right? So now that is the actual conventional method of building a project, right? So usually what happens in programming, the sequential design is you have a problem statement and then you pass it across to various departments or the domain or the teams which will be implementing specific tasks, and then the output of all these teams will be ultimately integrated also, right? So here the disadvantage is each different team will be using different softwares for them to work with, right? And it is very difficult to integrate the outputs of all this, right? So one more disadvantage is suppose there is a fault which is in the first stage itself. So in the problem statement or the requirements phase itself, there's a small error, right? And that has been captured for across the next years, and then they would have integrated it and developed it. And if there is a small change in the requirement again, so they'll have to go through the complete iterations again from the first, right? So which is very time consuming, and it is very cost ineffective for the companies to work on such designs, right? So that is where model based design comes into picture, right? So especially MATLAB is a very good tool for model based design. uh, what you get there is you get access to all the departments across engineering, and the models in the MATLAB environment itself, which can realize these type of systems uh, within the MATLAB environment, right? So what happens there is each department here will be using MATLAB as a software for their specific development, and uh, it is completely integrated. So everybody will be in one path, and you can actually complete workflow starting from algorithm design to realizing the hardware and programming it, writing codes, and testing it in the real-time simulations. Everything can be done in a single simulation model, which is Simulink, right? So what this helps is if there is any specifications change in the mid time, and if we want to add new things, we don't have to actually reiterate from the first, right? So the model is already there. All you have to do is add new models, keep on adding new models to it, and build upon that, right? So which is a very easy and time consuming and cost effective as well for the companies to work with. So that's why most of the companies are migrating towards model based design, and you get to work with model based design in many companies like Continental, Airbus, all the defense libraries across India, right? Right? So they majorly use the model-based design for their part, right? So this way they can save a lot of time and produce better design, low-cost prototypes and such, right? So this is a complete workflow for model-based design, right? So we have the research requirements, design, implementation, and integration, right? So the best part here is you see that there's a test and verification for each of these subsystems, right? So starting from the requirements to integration, each stage has a test and verification stage, which what it helps is in the building a compact and good accurate system, and everything is meeting the design requirements then and there itself, and only it is going forward, right? So this helps in good productivity and good designs and increase the overall performance of the design, right? So this is the usual model-based design workflow, right? So this is some of the key features of model-based design. You can increase your math and algorithm content and eliminate hand coding and such. You can go through these, right? So MATLAB also, Simulink also has a lot of support for hardware. You can directly integrate Arduino. So all you have to do is just install the support package for Simulink. And if very similar to how you work with Arduino, right? So suppose if you want to use one of the digital pin to read input, you just use the read digital pin block. In fact, I have the block also here, right? So these are the common blocks available. Right. So if you want to read an analog input from a specific pin, just drag and drop this block to the model and specify which pin you want to work with, and it will capture the details from that pin from the Arduino real time and give you the output to the Simulink window. And in Simulink, you can perform some operations such as your algorithms and work with it. Right. Similarly, you have support for many things such as internet, motors, and you can model sensors as well. So these are all accelerometer, parameter sensors. That is a good question. Simulink is only to simulate or can implement it in real-time application. Yes, it can be implemented in real-time application as well. So the Arduino Simulink support package, what I'm showing here is it can capture real-time data, and you can also push in your data from your Simulink models here. You can perform some signal processing application or processing algorithm here. You can capture the real-time data from Arduino, you can process it, and the results you can again push it back to Arduino and give it to the external world. Right? So it can be used as a real-time application also, apart from simulation. Right? So that can also be done. So similarly for Raspberry Pi, you have support, and you can also deploy your Android and iOS devices. You can develop your APK applications, mobile Android Studio applications directly using MATLAB. What it does is it calls the Android Studio APKs or the support packages and builds a wrapper upon it, and then builds you the complete GUI on iOS or Android devices. All you have to just use a USB to connect to your laptop, and you can dump the complete application on your phone, and you can do real time. You can actually capture the phone sensors, mobile phone sensors such as gyrometer or camera sensors or many other sensors. You can push the data to MATLAB and you can work with them as well, right? So similarly for Zinc SDR, so Zinc SDR is for simulating communication systems. So using the hardware, right? So you can actually transmit and receive and simulate real-time communication systems and calculate bit error rate analysis in a real-time environment and observe the performance using Simulink as well. Right. So I'll be showing you some of aspects of these things. If you have, feel free to reach out to me. I can help you out if you're working on any communication systems using any sync hardware. Right. So I would recommend. Actually was expecting you all to go through Simulink Conramp before this, but then even though if you have not gone through Simulink Conramp, please feel free to go through Simulink Conramp. It's free of cost, and it will roughly take 2 hours for you to complete the whole course, and you can access it in MATLAB Academy, and you can ramp up on your technical skills on Simulink. All right. So this is a small agenda I have for you all on communication systems modeling. Right. So I'll be talking on what are all the communication system toolbox features, and what are all the signal terminologies which you have to be using, and how does the signal represent in the communication system model, and what are all the sources. And I have an example of digital modulation where I'll be examining a QAM system, a transmitter and a receiver QAM system, and I will be subjecting it to environmental effects, environmental channel effects, and observing the performance of the system. Right. So let's see how we'll do that. Right. So these are all the key features of communications toolbox. Right. So you can it has algorithms and applications apps to for analysis, for design and end-to-end simulations. Right, so you can also do verification on communication systems. So the key features are you can use the waveform generator app to generate waveforms, custom waveforms, as well as standard protocol waveforms. Like for example, if you're working on 3G, 4G, or 5G, the transmitter has to be of a specific standard, right, to transmit and to get a specific data rate. So it has to follow some protocol rules. So MATLAB has a GUI where you can simply specify the parameters of your transmitted signal, and it will automatically give you the whole protocol packet which you can actually transmit through your communication channel. Right, so you can calculate the bit error rate. So once you transmit it out, at the receiver end, you demodulate the signal, extract the uh, bits from your received signal, and then you compare it with the transmitted signal and calculate the bit error rate. So that is what is bit error rate is, which we'll be simulating, which is a major criteria for us. Which a good communication system has less bit error rates, since it is traveling through a physical medium such as air or any other, it might be underwater, right, or many different weather conditions. You should not have error in bits, right, so or else you will not be able to get the accurate data at your receiver end, right. So this analysis will see how we can model and simulate, right. So you can also build receiver components such as automatic gain controls and DC blocking and carrier synchronizations and such, right. So it has good support for hardware. Like I told, you can connect your sync hardware, and you can do over the air testing. If you should be having some specific hardware such as FM comms, which is a complete suite, transmitter and receiver suite for you to test your communication algorithms. You can model a complete hardware system, which is a transmitter and also a receiver, which will work simultaneously and give you real-time results. Right, so you can also use GPU-enabled algorithms. So the receiver majorly uses LDPC and vertibi decoders, right? So it will need some computation time to actually decode and demodulate and give you the actual bits, right? So you can accelerate these processes by using the GPUs in the system, such as NVIDIA GPUs or AMD GPUs, which can actually improve the performance of your computations drastically. Right, so these are all the communication tool features which MATLAB has to offer. So how do you get started off with communication toolbox box simulating model? Right, so how do you start off is right, so just go to Simulink start page, right. So in the start page, what happens is in the communications toolbox here, you can click on communication systems, create a model, right. So this is how you should actually start off with your communication toolbox. Why? Because as you do that, so these are all some of the configuration parameters which are automatically set, right. So you see that the solver here is a variable step discrete solver, which is what the hardware systems are, which hardware systems are fixed step, right. So you can change this. So for simulations, so if you're working on hardware, you should be changing this to fixed step, right. And you have start time, stop time as infinite, because this is a continuous system. It will be running infinitely. As and when the communication data packets are received, it demodulates and give you the model, right. So your stop time is infinite, so it is a continuous real-time model. And some other parameters which are essential for you to work with communications modeling, right. So to start on, right, you go to the Simulink model. Right, so this is the model which you get. Right, so how do you do that? MATLAB, Simulink, and go to the communication systems toolbox and communication systems. So this will create a model for you. Right, so it will create an untitled. So this is how it looks, and here you can actually use the library cursor to model some communications models here. Right, so you can do some modulations, you can do some source coding. Right. Uh, you can use the sequences to work with. Right, so MATLAB also has some of the random sources and sequence generators which can be used for source generation. Right, so if you don't have, since you're simulating, you want the real-time data to be coming in, right? So these blocks will help you in generating the random data which can be given as an input to your, right? All right. So the terminology here, so how the signals has to be represented. So usually we know the MATLAB is completely built on matrix, right? So which is an n cross n matrix. So the default data type for MATLAB is of double data type, right? So and its size is and if its size is 1 cross 1, it is a scalar element, right? So usually signals are of sample based processed. Right, so each samples you'll be populating it and creating it an array. Right, so there is a stream of data coming in. Right, so it has to be, if you want to realize the model, so it has to be either as a column vector or as a row vector. So column vector is a single column with n rows, and a column vector is a single row with n columns, right? So, your input signal should be represented either as a row vector or a column vector. So, if you're working as a working with simulating, make sure that your data is majorly of the type column vector, because simulating majorly works on column vector type of data. So some of the blocks will throw you an error if you are giving the row vector as an input and such, right? So make sure that your input data is of a column vector. Right? So let me just show you how the input looks like. Right. So so this is just a ramp signal, right? So if I simply plot it, we'll get a complete ramp signal. So I have 10 points starting from 0 to 10. Right. So if I have, so I have 10 samples here as my data, right? So that is my input data, that is my input signal here. So now this is a row vector because it has only one row and 10 columns, right? So this is a RAM signal, right? So I have 10 points here in between. Okay. So the column vector is a dash, right? So it has to be like this. So all your signals, all your samples should be as a column vector, right? So you have to make sure that you keep this in mind. So major of the signal blocks will work as a column vector here. All right. So that is the signal terminology we should be following. All right. So we have I talked about the different sources and sync. Right. So when it comes to phase modulation, we have different techniques of phase modulation, like amplitude modulation. Oh, okay. So when it comes to amplitude, you have different types, right? Like for QAM and uh, PM. So for phase modulation, we have PSK, DPSK, OQPSK, and such. So these are all different phase modulation techniques which are already available. And right now, OFDM is currently trending because 4G and 5G uses OFDM, which again has a lot of disadvantages. And if you go further, right, so 5G is majorly on OFDM, so which they have found out that it has a lot of issues when it comes to data speed and environmental issues. So there is a new technique which is going to replace OFDM as well in the coming upcoming generations of mobile network. Right. So today what I'll be doing is I'll be simulating 256 QAM transmitter receiver model, right? So I'm subjecting it to additive white Gaussian noise as well as phase noise, right? And I want to see how the performance of bit error rate is when I change these environmental parameters. right? So I have a rectangular 256 QAM to which converts the randomly generated binary data to analog form, and I'll be passing it through a Gaussian noise channel and phase noise channel, and I'm demodulating it, and I'm calculating an bit error rate here using the error rate calculation block. So I'll be getting three outputs here. So what is the bit error rate, and how many total number of errors were observed, and how many symbols were compared, right? So these are the three inputs which I'll be getting from this block. So let's see how we can model these systems. So this is the model I have here. So you people all can also use the same. You can build the example uh, in your system. So if anybody is working on the examples here along with me, so you can go to MathWorks. And this is an inbuilt example. You can work with that, and it is a simple example. And this you can actually work on it and build upon, and you can actually implement a QPSK or a BPSK signal transmitter receiver, and you can implement multiple different decoding techniques such as Vertify. You can do block processing. Many communication support is also present. And so how do you get access to these? This example here is it is part of the communication toolbox example, right? You people can do it along with me. I'll just explain you how this works. Right, so it is in the documentation. If you can go, it is a shipping example. It is in the documentation. Go to the communications toolbox and click on examples. You'll get this model here, right? So if you want to execute it, you can. Uh, I'll actually put this command in the chat window. You people can execute it in your MATLAB. All right. So yeah, so this is currently simulating. Let me show you how it works. Right. So here I have the Bernoulli binary generator here, and these are the parameters which I have set it. Okay, so now this is the bits per sample. So this is for QAM. So why that I have put it here is, so in the rectangular QAM, I have mentioned 2 power NBEPS, right? So which is my M array. M array determines what value QAM you are using, right? So if it is so since my value here is 8, so 2 power 8 is 256, right? So I can actually reduce it to 2 power 2, and this will become a QPSK now, QAM, right? So for a quadrature, yeah, this is for 256. Now it will get changed for 24 points you'll have, right? The effect of the on these systems, right? So it generates, so what the Bernoulli binary generator block does is it generates a signal consisting of 60 sequences of 8-bit binary values in the range of 0 to 255, right? So then the QAM model, it modulates the binaries to In log form, it is then subjected to additive white Gaussian noise, which the signal to noise ratio is determined by EB by N naught, which is my parameter here, right? So currently it is around 35 decibels. Okay, so which is the additive white Gaussian noise which I'm adding, and I'm also adding phase noise. So phase noise, again, frequency offset, and the phase noise level is the parameters which I'll be using to set the parameters. So frequency offset and phase noise here, right? And this is again, it should be the same as the input, right? So what this does is it takes in the analog signals, convert it to binary, and each frames here is limited. So here I'm also setting one more parameter as target number of errors, right? So I'm telling it that if I have 1,000 errors, just stop the simulation, right? And stopping the simulation if I reach a maximum error of 1,000. All right, so let's see how much time it takes to simulate. Right, so now here the bit error rate, once I simulated, I have 490 errors, and it has reached a total number of error count. Right, we saw here. So these are the total number of symbols it has calculated, and what is the bit error rate and such. Right, so here what you can do is you can actually play around with the values of EB phase noise and AWG noise, right? So which is the EB by N naught parameter and phase noise parameters, right? So if you can simply play around here and see how so if I increase the signal to noise ratio, or for example, yeah, and I the phase noise also, if I'm increasing it somewhere. Right, so this will again affect on the performance, right? So now if I have harsh conditions, then my signal will not be able to walk through, right? So I'll just change the, right? You saw, see, this is the output of the phase noise here. So this is how my input data is, right? So this is the QM with the AWGN channel. So again, here my signal strength is good, but then due to phase noise, I can see that my data is completely jumbled across, right? So I will not be getting a good error here, a good PER value here, right? So this is one way where mathematically we can see, but then this is how not BER is calculated, right? So to calculate the bit error rate, so normally we follow a physical model to actually work with, so which is called a Monte Carlo simulation, right? So what this Monte Carlo simulation does is it actually has the complete set of parameters required for a complete end-to-end simulation. So starting from uh, a transmitter end wave, what is the PN sequence it is using to scramble the data, what modulation technique it is, what is the actual signal to noise ratio after AWGN channel, and how is it affecting the data, right? So the whole thing can also be done in MATLAB, and that's what I'll be showing you now, right? So for you all, if you're working, so just type BER tool in the command window, and it will open up the bit error rate analysis tool, right? So here, close this. So here you can actually have model the complete theoretical model as well as simulate it using a practical model, right? So if the behaviors, if you are simulating it on a Monte Carlo model architecture, you can be sure that the output of the hardware system will also be similar to somewhat the performance of the Monte Carlo, right? So for you to show you how the Monte Carlo model looks like, let me just show you the example. Just a minute. I just want to show you how a complete architecture of a model that you have why I'm using the model and what am I trying to achieve. Yeah. So now this is a typical communication system. So this is a direct sequence spread spectrum system. What I have here, right? So, but the interested model is the Monte Carlo model here, right? So, see, we have parameters here. So this is a complete simulation, end-to-end simulation, right? So we have a signal, input signal, which is multiplied with the PN sequence, right? So then it is added with the Gaussian noise if there's any other interferences. uh, you can also model them and the same sequence. So now this is the receiver, right? So the receiver also should have the same PN sequence to demodulate the signal, right? So then the output is actually collected, it is compared, and then the error is given out, right? So based on the receiver algorithm. So there are multiple receiver algorithms for many different cases, right? For a specific type of modulation technique, there is a demodulation technique as well, right? And there is a demodulation scheme and architecture as well. So for those systems, you can use the Monte Carlo model to simulate the complete system and calculate the bit error rate. And this is how the bit error rate looks like, right? So as and when there is an increase in the signal to noise ratio, right? So we modulate signals with different parameters and try to find out the. So here, for example, I have a signal with amplitude of or the specific parameters. So what this means is as and when my signal to noise ratio is increasing, so which means that my noise signal is increasing. So you can see that the bit error rate is also increasing a little bit. Right, so 10 power minus 2 means for every 100 samples, I have roughly around 2 to 3 bit error rates. Right, so that is what this means. Right, so it depends on the signal to noise ratio, and that is what we'll be verifying here. Right, so let me first theoretically model this. So I have a signal to noise range from 0 to 9, for example. Right, and I want the channel type to be AWGN and suppose I want QAM of modulation 4, right? So you can also do a channel coding if you have a convolution channel coding and convolution codes if you are using as for transmitting and receiving. So you can use the convolution one. So currently I'll just use no channel coding here, and I'll click on plot. So what this does is, so it makes use of Simulink model. It makes use of a complete uh, model like this, what I had opened, right? So I'll also show you what model it is using. So this is a theoretical curve as in when the signal to noise ratio increases. So this is how the B or bit error rate is expected to uh, behave. So similarly, I'll do the same for Monte Carlo here. So I have 0 to 9, right? And what is the simulation model? So here, so since this is an application, so you can either have your custom Simulink model here as an input, or you can use the existing Simulink model for working with it. Okay, so this will be in, so by here in the browse, I'm just taking the inbuilt examples. All right, so that's why I'm going to the MATLAB. Just right, so I just want the location of the program. MATLAB. Right, so these are all already the inbuilt examples what I have. So I'll go to browse. Right. So here we have for many different. So I can use a basic implementation of the model. What I'll do is I'll also show you what models I'll be using. That way you. So what this is a communication model, right? So this uses QPSK, right? QPSK modulator, demodulator, AWGN channel, and transmitter receiver bit error rate calculation. So similarly, if you are using for turbo codes, so there is an inbuilt example as well for that, right? So if you double click on turbo here, so this will give you a complete uh, model for turbo codes. Similarly, if you are using Vertify decoding for your convolution codes, right? So you can, there's again an example for you. So if you can model Rayleigh fading also for OFDM. So these are all different inbuilt examples already available for you all to work with. Right. So this is a turbo encoder and turbo decoder example what you have. Right. So similarly for convolution, you have Vertify, and with the AWGN, you can explore these, and I'll be taking these specific examples, right? So this is a convolution encoder, and this is a Vertify decoder, right? So you can use this model. So these are all inbuilt models. So that's what I'll be using here. So I'm just providing the path here. So you can see that this is actually the physical simulation which I'm trying to do, right? So this is a basic model here. And what is the BER variable, and simulation limits. I have how many number of errors I should be having, and how many number of bits. So if I run this, so this will again run the simulation for 9 times for each of the EB by and not range, right? And this is again working very good according to me, right? So if you choose a convolution type, all right, and if you plot, you can see this is the expected plot if you're using convolution coding for your communication channel. Right. So similarly in Monte Carlo, you should be using a Vertify decoding. Right, and run. So you can play around with this. You have a lot of examples here, and you can plot it. So this might take some time. So because it is simulating for multiple uh, times. And this is how you can, so you're basically getting the bit error rate here, right? So for each communication system, you're calculating the bit error rate and you're plotting it for different signal ranges as well, right? So this is how you can majorly work with the communication system. So this is an end-to-end system. You have a transmitter, you have a receiver. Now you can play around with the architecture, how you want to sample the data, how you want to form the packets, how you want to remodulate it. Your own custom algorithm, if you're working on communications, you can work with it, right? So we saw how we can model a Simulink model, and we saw how we can calculate a bit error rate using the BER analysis tool, right? So then there are many other tools as well when it comes to communication systems. You can model multiple types of systems, and multiple applications are there as well, right? So I'll just stop this. Right. So what this is doing is you saw that it ran the whole simulation taking into consideration EB by E naught, this value range, right? This is 0, 1, 2, 3. So this is a signal range, and other than that, for each signal range, it calculates the bit error rate, the performance of the system, and then calculates and plots it out. Right. So this you can, if you for documentation, majorly for researchers, you would want who are working on communication systems, you would want the BER curve to evaluate the performance of the system. Right. So this tool can help you in accomplishing these things. Right. So any questions for me? Please feel free to ask. Anyhow, we are running less in time. So I have one last things which I wanted to show you. Right. So this is the wireless waveform generator app. So this is an app where you can generate waveforms of these standards. It might be for LTE or 5G or any protocols if you want. So suppose for Wi-Fi, if you want to generate a standard waveform, right? So this is a waveform generator app where you can actually generate waveforms based on your inputs, right? So once you generate the waveforms, you can also export it as a MATLAB function, and you can use it as a source block as well for your simulations and verifications of the data. All right. So this is the waveform generator app, right? So here on the left-hand side, you specify the specifications of yeah. So you can specify what are the functions, what are all the parameters of your waveform, right? So that you can select it here. So either you can generate an uplink for 5G or downlink for LTE. You can model your Wi-Fi systems, which is on and also wireless protocols such as OFDM, TSSS, OFDM, and other things based on different standards. You can also do Bluetooth low energy packaging, right? So for a simple basis, let me just take PSK or QPS PSK, and once you click on the intended waveform type, so on the left hand side you'll get uh, parameters for which you want to model it. So for it is a 4 PSK signal which I want to do, and these are all the input bits. You can also specify your own custom input bits. So here it is just taking out zeros and ones of 60,000 samples. Right, so this is a 60,000 sample signal, and I'll click on generate. It will generate either zeros and one of 60,000 samples. Right, so once it generates the samples, here you can see the spectrum analyzer as well, and the constellation diagram of the model. Right, so this is a complete waveform, and you can click on export to workspace. You can export it as a signal file, or you can export it as a MATLAB script, and you can use the generated data to verify, test your communication system models or any signal processing signals. Right, so on a specific uh, type of data, you have modulated it, and you have created a waveform of a specific configuration. Right. So the best part of this app is if you are working on hardware, right? So unfortunately, I don't have a hardware to show you a demo like this. But then you can click on a transmitter here, and if you have the suitable hardware to work with, right? So you can find the instrument here, give the IP address or the domain name on the drivers, and you can directly send it to a hardware transmitter without actually worrying about coding anything, right? So here you will specify all the things required, and using this GUI, you can connect the hardware, specify the type of input data you want to transmit, and you can simply click on transmit. It will transmit it over the hair. So now all you have to worry is about your transmitter is already ready. Now all you have to worry is about developing your receiver and performing some changes and optimizing it. Right. So this is one app which you can use, and there are many other apps if you are working on communication systems. Uh, Signal processing, you have many apps here if you want to work on this, right? So you can explore this, and if you have any questions, you can reach out to me. I, uh, if I'm not aware, I'll get in touch with MathWorks, and I can get you some answers and documentations for them as well. right? So, so this is what I had for you all when it comes to signal processing and the communication systems, right? So these are all just the uh, impairments and such. So yeah, you can also add impairments and other channel effects to your waveform generator application, right? So what we saw today was we examined how to model a 256 QAM system in Simulink. We also saw how to calculate the bit error rate analysis for your custom applications, as well as uh, for the examples what I had today using the bit error rate analysis. And finally, we talked about how we can transmit it on the hardware using the waveform generator application. All right. So I'm sure there are many other things to cover. So this is what I had for today. And if you have any questions, please feel free to post it in the chat window. And yeah. So there's a question. So can I access or modify the basic element model of a block in a communication system toolbox? Which you can do. All the Simulink blocks, you can edit it. Some you might have access to, some you might not have access to, because those are all proprietary. You won't be able to get the actual code through which the model is, for what the model is implementing. The actual source code you won't be able to get. But then you can create your own Simulink blocks if you are asking that. Or if you want to modify the same element, I doubt we can do that, but then let me try. These blocks here, which come as the block sets here, right? So they are written in Simulink language, and I don't think you can completely edit the blocks here. So for example, QAM, right? So I don't think we can completely edit the model properties here, but then you can change the parameters only, right? So, but using these blocks, you can build your own custom Simulink block. So using all the Simulink blocks you have here, you can build, using these blocks, you can build your own custom blocks as well. That is possible. So this base code, I don't think you'll be able to get. Yeah. So do I have any more questions?
Thank you, sir. I request Nandini ma'am to put forth some Q&A. Q&A.
Sir, we have got couple of questions here. I'll
Yes.
read off for you. The first question, for the benefit of students, if you could tell us, learning the various toolboxes will be an advantage during their career?
Sorry, ma'am, if you can repeat.
Yeah, for the benefit of students, if you could tell us, learning the various toolboxes will be an advantage during their career, sir.
Yes, ma'am. So, what in engineering, in fact, you all faculties opt for the students to do is to not use the toolboxes right away and develop these toolboxes on your own, right? So, but then once you have developed it, you can come back to MATLAB, you can verify whether your developed is working as expected or not. So in that way, if you take learning these will help them enrich their concepts, and to which you can apply these on your intended interest in your careers as well. So these are all, if your concern is whether these will help me in my career, so all the block sets which are being developed here are uh, uh, by consulting with the industries itself, they have come up with these block sets, and they are using these block sets in the industries as well, right? So that was your question. So this will definitely help you all in your career. In a technical sense. So if you are a developer, right? and if you want to model, and if you are a keen enthusiast, and if you want to see how the behavior works, and if you want to explore, then it's a very good tool. You can explore it. You can work on multiple domain and multiple domain applications, and it's completely up to you how you take it up.
So the next question, which companies require such toolboxes expertise?
Which companies? I mean, specifically, I'm not sure, but then I have a small slide for you all just to show you. So I just want to show you which are all companies are there. So, I mean, you're specifically asking for communications toolbox or all the toolboxes on the whole one?
Especially for communication toolboxes.
That is again, I mean, the companies, I mean, for example, all the defense lab like ISRO, DRDO, and LRD, so they all use communications toolbox for their prototyping. In fact, the CDAC, again, there's a research institute in Bangalore. So there are many companies which work. Airbus is there. Airbus works. Continental again uses communications inside vehicle communications, machine-to-machine communications. They use Huawei and Google uses. So wherever which and all companies has a potential of developing communication systems prototypes, they use it for their verification. I'm just not finding one slide which I wanted to show you. But then, yeah, it can. Many companies are there, ma'am, which uses it. So these are all some of the demos which, if you want, I can run some videos for you all just to show you how MATLAB is used in the industry and such. Yeah, so these are some of the major companies where you can expect to work with MATLAB. So these are only handpicked, very little companies, but there are many more companies which use MATLAB, not only in India but outside as well. Like so, Lockheed Martin is for aerospace, right? So Rafael was developed by Lockheed Martin, right? So and Dassault Systems, right? So they all use MATLAB. So there are many companies which use MATLAB. If you are keen on knowing what they use it for. I hope I answered that question.
Yes, sir. Yes, sir. Sir, my next question. Could you suggest some area where final year students can undertake project work using MATLAB or something?
All right. So for that, just to motivate you all, I have a very good video. I'll just play a 1 minute video, if I may. Can I play that video now? Just to give you all an idea. Hello.
Yes, sir.
Just let me know if you hear the audio. I am not getting an option to optimize it for. Just tell me if you're able to hear this video.
No, sir.
Not able to hear my audio, right?
Yes, sir. No, sir.
Okay. So if you any idea in the for the electronic students, ma'am. So this is a question from which department?
Yes, sir. For the electronic students, sir.
All right. So,
Also, this can be applied to electrical students.
all right. Sure. All right. So here in the MathWorks website, if you can go to solutions here, right? So here you get to know how MATLAB can be used and for what all domains, right? So for electrical department, power electronics is a good area of research as well as for development, right? For electronics, control systems are there, and ASIC for FPGA development, where you can actually develop your Simulink models using system generator and actually work on hardware, right? So this is first thing. So you have image processing and computer vision applications. So in fact, we are actually conducting an competition on computer vision. So I can send you the registrations for this month. So basically the idea is we'll be giving, it's on machine learning, and the students who get shortlisted will be getting a chance to develop a computer vision application, and we'll be training them on that as well. And top three will be selected there as well. So depending upon how good your model is and how robust it is, I can send you the flyer now for this competition. You
Okay,
can spread
sir.
it across for your students and you can register as well.
Sure, sir.
If that is for image processing and computer vision, right? So you can do data science, which is AI, machine learning, deep learning. You can work on Internet of Things. Robotics is also there, right? So for signal processing. So signal processing on the whole, if you see, the major application areas are on medical imaging or sensor acquisition systems and real-time RTOS systems, where you'll have to actually build a complete real-time operating system, a complete hardware which works on real-time data inputs and outputs. All right, so these are all some of the applications which are already there and which MATLAB can be used for you all to work on. So there's no limit as such. So it's up to you how you want to put in your domain skills, what you have learned, and put it to practical use. Right. So this is where I think this page will give you a complete idea of what all applications are there in the MATLAB. I'll just put it in the chat window as well, the solutions. So is this what you were expecting, ma'am, or specifically?
Yes, yes, sir. Yes, sir.
All right. All right. Yeah.
Can I take up next question, sir?
Yes, ma'am.
What are the minimum skill set required to become signal processing or communication design engineer, sir?
Okay, so minimum skill set is basic understanding of signal processing, especially sample-based and frame-based processing when you're working with signals. And communications means the complete idea of front end as well as how the signals are transmitted over the air, and these block LDPC codes or block codes, having codes, right? So these things will be, so if you see, if you come down, it's ultimately information theory and coding, right? So all the signals, all the communication systems work on information theory. So if you are good at information theory, I think you can work on either of these departments. So everything boils down to ITC and coding, right? So these block codes and which you all study in your engineering, right? So if you're good at ITC, I think everything else will be a very simple task for them.
Okay, sir. What are the add-on packages required to connect low-cost hardware?
All right. So there are to get to know what are all the low-cost hardwares which are available. Just go to MATLAB window and click on add-ons here. Right. So for hardwares, if you specifically want, click on hardware support package. Right. So this will give you a list of all the hardwares support packages available for MathWorks for your current version. Right. So here you can explore these things. So low-cost hardware, as in right now, two things come to my mind, which is Arduino as well as Raspberry Pi. One more thing, low-cost hardware is USB webcams, right? So for these, you should be installing certain number of toolboxes. So if you type Arduino here, this will give you the MATLAB support package for Arduino hardware, sibling support package for Arduino hardware. right? So these two has to be installed if you are working on MATLAB and Sim. So this is for Arduino. Similarly for Raspberry Pi. So here again, you'll have separate for MATLAB, you'll have separate for Simulink, right? So you can MATLAB support package for Raspberry Pi, Simulink support package for Raspberry Pi. So whatever the hardware is, so similarly for MKR or any other Arduino library, so that is again covered by support package for Arduino, right? So if you're working on Raspberry Pi, these two support packages you'll have to install, and USB webcams. Your MATLAB support for USB webcams. If you install this, you can also access your laptop cameras. Also, you can capture a live video, live images from your USB webcam or your laptop webcam, and you can do some image processing or computer vision applications from there. Right. So, if you have anything specific, if you can mention, ma'am, so I'll throw some light on the support packages required for those hardwares.
Yeah, I mean to say that with respect to Raspberry Pi and Arduino, I was asked, sir.
Yeah, I mean hardware, Raspberry Pi and Arduino, MATLAB support and Simulink support for those.
Yes, sir.
Yeah.
Yes, sir. Sir, could you share some insight on student challenges on MATLAB and Simulink?
Student challenges and Simulink. So major, ma'am, so they should be aware of simple programming. It is very easy. This is a very high level language. MATLAB, it is very similar to Python. So it's like how you speak, you just write some codes, right? So they should, the fundamental challenges they'll face is getting access to the software itself. Right, so that is the only challenge I believe what they'll be having. But you people have eased that out, so they can use MATLAB online. So I don't think there's any issue in getting access to online. So they have all the trainings now. Your college students have all the training materials required. So they just have to make up their mind and go through these training courses, and they have everything. So I don't see any challenge for your students right now.
And the last question, sir, could you share some insight on MATLAB examples and Simulink example in academia?
All right. So as and when you go to MathWorks website here, at the bottom you have a section called examples here, and here you'll get all the examples, ma'am, for all the block sets, all the toolboxes, specific toolboxes types. So for example, communications toolbox. It has a complete set of examples starting, I mean, it is for everybody. I mean, it's like a public repository. It is starting from academia up until if you are an industry or a corporate guy and you are working on specific systems, up until them, that also you have examples, right? So examine 256 QAM is today what I just showed, right? So you can also accelerate your components, right? So here you can do error detection, and from a beginner to an intermediate to an expert, there are examples for them as well in the example section. So I can put also the chat. So here you can find toolbox related examples.
Okay.
Yes, ma'am.
That's all, sir. Thank you, sir.
Sure.
Hello.
Hello.
Yeah. So thank you, sir, for such a wonderful session and sharing your knowledge and expertise. So I take this privilege to propose a vote of thanks. So on behalf of SJC Management and Department of ECE, I take this opportunity to thank Mr. Shashi Kumar from Coral Technologies, Bengaluru, for the wonderful presentation. We thank for the insights about the signal processing and communication related toolbox, especially for students. Thank you, sir.
Thank you, ma'am.
Also, I thank the management of SJC for all the encouragement and support in organizing this webinar. I extend my sincere thanks to our dear HOD, Dr. Dakshini, for all the assistance in organizing this webinar. I thank the members of the panel, and a special thanks to Ms. Nandini for identifying the resource person and for all the arrangements. I thank Mr. Ragesh Raju, Ms. Bhagya, and Ms. Jacinta for the logistics. Most importantly, I thank the wonderful audience for their active and wholehearted participation. I request you all to kindly fill the feedback form. The link is displayed in the chat box. And thus we come to the end of this session. Thank you one and all. Have a great day. Thank you.
Thank you.